All right, consider the H2 plus ion. Sketch the molecular orbitals of the ion and draw its energy level diagram. All right, so with this problem, we're starting to get into what's called the molecular orbital model. So far, and for really 95% of what we're covering in this topic, we've been dealing with the localized model, or the valence shell electron model, where we take half-filled hybrids or half-filled unhybridized orbitals and overlap them, right, to get a high electron density between the nuclei, or in the case of pi bonding, overlapping outside the internuclear zone, right? So this is the way bonding occurs, right? We get half-filled orbitals overlapping to form a bond. Well, that's really good. It's a good model for explaining geometry, why we get the different geometries we do. Its shortcoming is why is potential energy lowered when I form a bond, or where do the electrons go when we break a bond, or why do we have certain spectrum for different molecules? I mean, just like atoms, you can get a spectrum for a molecule. No indication of where electrons go when they're excited. So when we get to the molecular orbital model, we're going back to quantum mechanics in terms of these distributions, right? So if I'm going to make the hydrogen molecule ion, I have two 1s orbitals, all right? So these are sphere shapes. And we're going back to the fact that electrons behave like standing waves. There's two interactions you can get when you overlap a wave. You can either get destructive interference, where you're lining up in such a way that you destroy the wave, or you end up with constructive interference, where you're amplifying the wave. So when we overlap two atomic orbitals, the way the molecular orbital model works is they disappear and they form two molecular orbitals, one bonding orbital and one antibonding orbital. All right. So the dots represent the nuclei, right? The black dots. With the bonding orbital, right, we've lowered potential energy. We've gone down to a lower state because we have a high electron density now between the two nuclei. With the antibonding orbital, right, with destructive interference, we have a very low or no electron density between the nuclei, and this is why an atom would split, right? Excite electrons, and now all of a sudden we've got a low electron density. Better to be in the atomic orbital form than be in the molecular orbital model form. So, or the molecular orbital form. So, destructive interference causes antibonding orbitals. Constructive interference causes bonding orbitals. So, getting rid of my cloud drawing, right? So this is my best rendition of what this looks like, right? So high density between the nuclei with a bonding orbital, low electron density between the nuclei with an antibonding orbital. Just looking energetically, right? The two atomic orbitals overlap, and we form a low potential energy bonding orbital, sigma bonding orbital, and a high potential energy sigma antibonding orbital. All right, so going back to the Aufbau principle, where does the electron want to be? Well, it wants to be in the lowest potential energy possible, so it's going to drop down to the lower energy bonding orbital. All right, so this is why atoms would bond, right? The electron wants to be at a lower potential energy, so it's going to drop into this bonding orbital and cause the atoms to stick together. Okay, so how many electrons are there in the ion? All right, one, right? So it's got a plus charge, so there's only one electron here, right, being donated by one of the hydrogens. Draw the electron configuration in terms of molecular orbitals, so that's what we've done here. What is the bond order of the H2 plus ion? All right, bond order is a sort of simple way of determining whether you have a stable bond or not. And the way it works is you take the bonded electrons, the number of electrons in the bonding orbitals, and subtract the number of electrons in the antibonding orbitals, right? So in the case of H2 plus, we only have one electron in the bonding orbital and no electrons in the antibonding orbital, divided by 2. So if I end with a bond order that's greater than 0, this implies a stable bond. If I end up with a bond order, 0 or less, like a negative value, this implies a non-stable bond, and the bond will break apart. All right, so E. All right, so here we are with our lowest energy possible, right? Suppose the electron is excited by light, all right? So if the electron moves from a lower energy to a higher energy molecular orbital. What would you expect the excited state of H2 plus ion to be? Will it be stable or fall apart? Explain. All right, so if we excite this electron, now it's up at a higher potential energy than the two atomic orbitals that made it, right? So the way energy works, right, we want to be at the lowest potential energy possible. So better to have the atom separate and have the electron in a bonding or in a atomic orbital than up in an antibonding orbital. So this is a reason why the atoms would separate, right? Put an electron up in an antibonding orbital, better to have the atoms separate and have the electron drop into an atomic orbital. So if I did the bond order for this, right, I have no electrons in the sigma bonding orbital, but I have one electron in the sigma antibonding orbital. Divided by 2, I end up with -1/2, and this implies an unstable bond and a reason why this bond would fall apart. All right, use figures 3.5 and 9.43, 35 and 43 as guides. Draw the molecular orbital configurations for B2 plus, Li2 plus, N2 plus, and Ne2 plus. In each case, indicate whether the addition of an electron in the ion would increase or decrease the bond order of the species. All right, so in order to write these electron configurations, we have to recognize again what's going on with molecular orbitals. When you overlap the 1s with lithium with the 1s of another lithium, right, we create two molecular orbitals, one bonding and one antibonding. All right, so the two electrons in the 2s of lithium so again, the core electrons is playing a part here, right? They're on the inside. So the two electrons in the 2s of the one lithium and the two electrons of the 1s of the other lithium go to create 4 electrons, right? And these electrons have to be somewhere. So 2 of them are going to be in the bonding orbital and 2 of them are going to be in the antibonding orbital. Now we go to the second energy level. Each of these lithiums has 1 electron in its 2s. So 2 electrons to account for. So they'll want to be at the lowest energy possible, so they'll appear in the sigma bonding orbital, not the antibonding orbital. If I was dealing with 2 berylliums to make beryllium 2, subscript 2, I have 8 electrons to account for, right? 4 electrons coming from one beryllium, 4 electrons come from the other beryllium, and they'd fill up the bonding, antibonding, bonding, and antibonding of the 1s and the 2s sigma bonds. All right, so notice again, right? Atomic orbitals. 2 atomic orbitals overlap. They make 2 molecular orbitals, one bonding and one antibonding. So 4 orbitals overlapping, 4 molecular orbitals, 2 of them bonding, 2 of them antibonding. All of them filled if you're dealing with Be2. Okay. Then we get to the P's. All right, if you remember, a P looks like a dumbbell. So if we're looking at the red dumbbell of the one atom and the red dumbbell of the other atom, they can overlap in such a way that they're overlapping between the nuclei, right? This is a sigma overlap. That means that the Y orientation and the Z orientation that are going into and out of the board here are going to overlap outside the internuclear zone. And this is how you get molecular orbitals pi bonding in the molecular orbital theory. So when the P's overlap, you end up with a sigma overlap. All right, so you end up with a sigma bonding orbital and a sigma antibonding orbital, and then you get pi overlaps. All right, so energy going this way, potential energy going this way. All right, you end up with a 2 PZ bonding and a 2 PZ antibonding orbital, and a 2 PY and a 2 PY pi bonding orbital, and a 2 PY antibonding orbital. Okay, so we get 6 orbitals overlapping, and we get 6 molecular orbitals. 2 of them sigma bonding and antibonding, and then pi bonding and antibonding. Okay. So if you're dealing with boron, right, we've got 6 electrons to account for from each atom. All right, I'm sorry, only dealing with valence electrons here, right? So the outer electrons, you've got the 1s filled, so we're going to leave the core electrons out of this, simplify it. We're just going to look at the valence overlaps. So we have the 2s overlapping to make a 2s sigma bonding orbital and a 2s sigma antibonding orbital, and we get the pi's overlapping in a sigma way. All right. So diamagnetism and paramagnetism come back, right? If we end up with orbitals, molecular orbitals, where the electrons are paired, we end up with a diamagnetic molecule. So molecules can be diamagnetic just like atoms can be diamagnetic. The thing of it is, though, when you run boron through the field, it doesn't come out paramagnetic, even though the sigma bonding orbital is lower in, or you have a higher electron density between the nuclei. Because you have so few protons in the nucleus of boron, you end up with all these electrons being shared in between the nuclei, and you end up with electron crowding, electron-electron repulsion. So better to have the electrons bounced out to the pi overlap, right, outside the internuclear zone. And energetically, for boron, this is better. This is the actual configuration, so boron is not a diamagnetic. B2 is not diamagnetic. Paramagnetic. All right. So, complicated, huh? All right. So let's get going. So this would be the configuration, right, where you're filling the pi bonding orbitals before the sigma 2p orbital for both boron, or for B2, C2, and N2. When you get to O2, now all of a sudden you've got enough protons in the nuclei of these atoms to have the electrons shared between the nuclei, right? That pulls the electrons back in between the two nuclei, and you fill the sigma before the sigma bonding orbital before the sigma fill the sigma bonding orbital before the pi bonding orbital. All right, so that's going to be the same for O2, F2, and Ne2. Okay, so paramagnetic for boron, diamagnetic for carbon, diamagnetic for N2, paramagnetic for O2, diamagnetic for F2. And, the bond order for Ne2 is so unstable, you don't end up with a molecule of Ne2. Okay. So B2 plus. All right, so let's go back to what the problem was, right? We were supposed to be dealing with a molecule that has one less electron than it should. So when I overlap, right, I've got 5 electrons to account for. 2 of them are going to go in the sigma bonding orbital, 2 of them are going to go in the sigma antibonding orbital, and 1 of them are going to be in the pi bonding orbital. So paramagnetic, when I do the bond order for this, I've got 3 electrons in bonding orbitals and 2 electrons in antibonding orbitals. So 3 minus 2 divided by 1 gives me a bond order of a half. All right, so this is a stable molecule. B2 plus is stable. If I added an electron, right, to make boron, I'd end up with an even more stable, right? I'd have more electrons in bonding orbitals and therefore a more stable bond order. All right, that's A. Looking at B, Li2 plus. All right, so I only have 1 valence electron to account for here, and that's going to show up in that sigma bonding orbital. So it's going to be a paramagnetic molecule. 1 minus 0 divided by 2 gives me a bond order of a half, so that's stable enough. And if I put another electron in there and get Li2, I get more electrons in bonding orbitals, and I get a better bond order. All right, so even more stable. All right, so that's the answer to B. Looking at C, N2 plus, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons to account for here. So they'll go in the lowest energy possible. So the sigma bonding will fill, the antibonding will fill, the pi bonding, and the sigma bonding will get the last electron. So it's a paramagnetic, right? We have an unpaired electron. When I count up the electrons in the bonding orbitals, I have 1, 2, 3, 4, 5, 6, 7. 2 of them in an antibonding. So 7 minus 2 divided by 2 gives me a bond order of 2.5. If I was dealing with nitrogen, I'd have more electrons in bonding orbitals, so I'd have an even greater bond order, so even more stable bond. And that's for C. For D, we've got, all right, so for D, we've got neon 2 plus. So by taking 2 electrons out of that molecule, Ne2, we have less electrons going into antibonding orbitals. So when you do the, it's diamagnetic, right? They're all paired. When you do the bond order, you end up with a stable bond order, right? So Ne2 2 plus is going to be stable. Whereas if you put those electrons back in, they're going into antibonding orbitals. And I end up with a bond order of 0. So unstable. So Ne2 is unstable, whereas Ne2 plus is stable. All right, for the test, you have to know how to fill in these molecular orbital configurations. You're given the skeleton of it. You just have to know that you're following the Aufbau principle, the Pauli exclusion principle, right? 2 electrons per space have to be spinning in opposite directions. Got to remember what the term diamagnetic, paramagnetic are, and how to do the bond order. Bonded electrons minus antibonded electrons divided by 2. A nice N.